Okay, good afternoon, everybody, and good morning to some of our international guests. This continues the ASEG Webinar series hosted by the ACT branch. I'm Mike Barlow, I work for Geoscience Australia, and I will be introducing Dr. Indrajit Roy and his talk today on computation methods in geophysics. Before we get to Indrajit, I would just like to give some housekeeping notes, please. Firstly, all of this could not be possible without our corporate sponsors who contribute significantly every year. That includes HiSeis, Total Seismic, VelSeis, Archimedes Financial Planning, Southern Geoscience Consultants, and Santos. We thank you very much. On the branch level, we have a number of sponsors too. I'm not going to go through all of them. And unfortunately, those sponsors don't cover the ACT. We'll have to work on that. Okay, going forward, Indrajit is going to talk for about 45 minutes on computations methods in geophysics. If you have any questions, please type your message in the little box that will come up under Q&A. And at the end of the 45 minutes, we'll have a good time to answer some of those questions. Just for your information, a couple of upcoming webinars. 23rd of June, we have Majaba Rajabi talking on the contemporary crustal stress pattern of Australia. And that's followed on the 18th of August at 1 p.m. by Alberto Aded Segura, talking on lithologically constrained stochastic magnetotelluric inversion for imaging shallow conductors in geothermal fields. Quite a mouthful there. Okay, so for advertising for the ASEG, just keep in mind that we're always looking for new members, and one of the key benefits being the free access to exploration geophysics, one of the highest quality technical journals in exploration geophysics in the world, and along with all those other benefits and goodies that are available through our ASEG membership. And please keep in touch. Monthly email newsletters, our HTTPS site, Facebook, ASEG News on LinkedIn, and YouTube ASEG videos. We are out there. Thank you very much. So, I'd like to give a quick introduction to Dr. Indrajit Roy. He completed his Masters in Applied Geophysics from the Indian School of Mines in 1985. He went straight into a Ph.D. at the same school, and following his Ph.D., he worked as a lecturer at the Indian School of Mines. In 1995, he worked as a visiting scientist for the Department of Exploration Geophysics, Curtin University, before shifting to the Institute of Geophysics, University of Texas, as a postdoctoral scientist. From 2005 to 2015, he worked with Geoscience Australia as a senior research scientist prior to moving on to his own consultancy group as a principal scientist with Space Age Consulting. He brings to the talk today, and he brings 20 years of experience in potential field data processing, imaging and modeling, seismic data processing, inversion, electromagnetic and magnetotelluric methods, scientific methods in policy making, geoscience education and research. And this is followed through with 33 articles published and peer-reviewed, along with 58 extended abstracts and published. Okay, so you're all very welcome, and I'll hand it over to Dr. Indrajit Roy to talk about computational methods in geophysics with specific focus on derivatives. Thank you, Indrajit.
Actually, sorry. It is like that. Well, this will be the blueprint of my talk. It is a prologue that will cover what an audience would expect to listen, some examples demonstrating in potential field data interpretation, challenges and difficulties, and description of some strategies to mitigate such challenges, emerging concept in derivative estimation and its application. In this presentation, I'll show some powerful examples. Some technical aspects will also be covered. Audience may expect to see some mathematical explanation. Here is the potential field worms, as it fondly calls by the geoscientist. And these wiggly lines for both gravity and magnitude, which is being prepared and mostly being used at Geoscience Australia and possibly across the country, where Dr. Peter Milligan has tremendous contributions. But how such type of picture or the image can be prepared? GA-based procedures for preparing worms are basically generate that 2D distributed gravity and magnitude data. So you have a scattered data and then you distribute it in a evenly spaced grid, generate a map, then do upward continuation to a predetermined various levels, compute total horizontal gradients corresponding to each continued level, then use a Kenny edge detecting filter to find the maxima of the horizontal gradients. And those points of maximum are connected to nearest neighbor algorithms to joins and to prepare the worms. That's the general GA procedures, but others procedure available as well. But this is a procedure which is being adapted in GA during my time at least, and where Peter Milligan has had a tremendous contribution of generating this methodology and the software. But the most important part of is the generation of evenly spaced grid of magnetic data. So generations of map requires, from the scattered data, requires a smooth function, 2D function to be defined over. And that means it's an interpolations. And so for such interpolations, most important aspect is the smoothness to be preserved. And the function should be a continuous function. But and most important part of the smoothness function is that it should be continuously differentiable almost everywhere, and which guarantees the smoothness of the continuity of the functions. So keeping this thing in mind, the most important, powerful methods which has been used as a conventional way, most in majority of the software, is that Briggs minimum curvature algorithm by Mr. Ian Briggs, who was also at Geoscience Australia sometimes back. And Ian Briggs came out with a concept called that minimum curvature, where he considered that the smooth surface can be considered as a plate, an elastic plate, and their bend, their moment, bending moment will be considered as the constant. And he came out with a biharmonic equations, differential equations. Those differential equations can be solved either by finite difference, or can be by interpolations, or by a Green's function approach. So that's the way we generate the smooth functions. But most important thing in that you have a derivative of fourth order differential equations. And that means the derivative has to be there. So derivative is in the beginning of even in the worms generations. One may ask questions that derivative, is it essential for interpolation to generate smooth functions? Well, answer is yes, but you can see the examples. There are 3 such examples where the left-hand side is the no derivative, only a nearest neighbor approach, then bilinear with the first order derivative as a constant, and then bicubic where a third order derivative as a constant. So as you go higher the derivative, more smoothness is prevailed, and therefore it is rather higher order derivative is more acceptable for getting a smooth functions. Let us come back to that. How do you generate the worms? To estimate horizontal gradients of first order total or first order total derivative is the most important aspect of generation worms. See the curve over here. This curve has a maximum gradient at the point of inflections. So actually, from the anomaly curve, that maximum point of maximum gradient is chosen, and that all those points make a ridge lines. The ridge lines, and these ridge lines are connected to generate the form, generate the magnetic worms. Power of derivatives can also be seen that determining the edge or identifying the edges of the source body. See, here is a distributions of 4 prisms at different depths. Z0 is the depth of burial, and ZB is the depth to the bottom. And this white one is that with a positive density contrast, and the gray one with a negative density contrast. And you take the second derivative map, you find beautifully those all 4 images are observed, clearly observable. You can find out. So higher the derivative, the resolution is increasing. Very tempting. Next, we can see that not only the derivative is not only for image-based interpretations, where we can, all geoscientists can be very interested with majority of that image-based interpretations, qualitative, but derivative can also be take part in a quantitative interpretation as well. For example, like Euler deconvolutions. We are using that Euler deconvolutions where it is a 3D Euler deconvolution equations, and note that x0, y0, z0 are the position, location of the center of the body. Del G del X, del G del Y, del G del Z are the 3 components of the gradients, and S is the structural index. Normally, structural index for contact will be structural index for -1, 0, 1, 2 are different for the contact, dikes, cylinders, etc. So if we can put the structural index there and then use that Euler deconvolution 3D, then we can generate the map. So here the left-hand side is a Booger gravity map, and then Euler deconvolutions gives the depth distributions of the sources in the right-hand side. Derivative can also be used in a parameter, improved source parameter imaging, where you may not require exactly to define the model. Like in the source parameter imaging, you can get a first order local wave number, which requires that gradient, del M del Z, del M del X, and or second order local wave number, both you need, in fact, del to del M Z square, del to X square. There will be some mistakes here, X square. So here, using that wave numbers, K1 and K2, you have this formula, and from that you can directly interpret some of the things like that. That database interpretation with the improved source parameter, where you can use K2 and K1 to determine the depth of burial and structural index, and beautifully, because the peak is very clearly very conspicuous, very distinct, provided K1, K2 are determined in a very, very robust manner. We can see that derivative we have already seen that derivative has a power for not only for imaging, but also for interpretations, database interpretations, which we normally do. But there are some challenges in derivative estimations, like demand of precision in derivative estimations. Normally we need that, especially for sensitivity metrics in case of inverse problems. Demand in robustness in estimating of derivative for noisy data, because as we find the data is not always smooth, we have to have always some kind of noise, and derivative is very sensitive to the noise. Demand of computational efficiency, and another challenge is our modern demand of say with a machine learning or deep learning process, so that automations, so that we can do it in a very fast. So new concept in derivatives in estimation technique. These are some challenges. Let us talk about the precision. So most important thing with the in derivative that we know very quite often in general is a difference scheme. We start with the Taylor series. Brooke-Taylor actually developed these things in the beginning of the 18th century. Brooke-Taylor was Cambridgian, and he was a Newton's prodigy, you can say. But the Taylor series was later coined not by Brooke-Taylor, but an Austrian mathematician called Simon Levillier. Simon Levillier, who used the terminology Taylor series. So in Taylor series, what we find that if you had a small perturbations in a argument of a function f(x), then you can put it in a series form like f(x) plus h. H is the perturbation, is f(x) plus h first order derivative of x, then h square by factorial to second order derivative of x, and then etc. carry on. Similarly, if we do a perturbation in a otherwise minus, then the series having alternative negative, positive things. This series is a converging series. That's most important. So for generating that all that finite difference equations, suppose it's the central difference operator, what we find that it is very simple. F of x minus h minus f of x plus h by twice h. That means you have the x coordinate is right hand side little bit perturbation and left hand side little bit perturbation, and divided by perturbation amount, you get this central difference formula. And the accuracy in the order of our first order derivative, h squared. So if h is a say a fraction of 0, if it lives between 0 and 1, then it will be very small number. Similarly, for second order derivative is h to the power 4. Let us see in the next slide what does it mean. We can do these finite difference things in terms of polynomial. Why polynomial? Because my function is unknown. So polynomial is a function which is a smooth function, which is a very nice type behavioral function. So if we can look in terms of polynomial, then we can find out these functions with a say first order derivative with a say 3 points. Very simple. F1, f minus 1 is that one ahead, one backward, and n5 with the fifth order stencil, we're having say you require some point f of minus 2, minus 1, f1, f2, etc. And if we, why do we need a third order or fifth order? What are the advantages or what is the disadvantages? If we can check this figure, if I take the spectral estimates, that means what is the component of the spectra, then we find that this straight line is that ideal situation where there's a resolution is high, right hand side is scaled wave number, and it is a modified wave number. As we go on increasing that my order, like third to fifth to sixth, seventh to ninth to 11th, and you find that peaks are going and attending to this highest resolution. So if we increase the order, the spectral content on the derivatives becomes more. But that is a problem. So we cannot go, because more ordered it is, that stencil becomes larger, and then a large number of points will be there, and you have a problem sometimes with your endpoints. So there is always a compromise that will always make how big or how small the stencil could be. Okay. Now I'll show you something that for a synthetic examples, why derivative is necessary. Derivative is basically to increase the resolution. I take a very simple example of mixture of two Gaussian spectra. This is very commonly being used in case of in the spectral estimates, in other field in remote sensing. But this type of anomaly is a very ideal situation. What we find, these spectra, this bell-shaped curve that we had seen, actually of the two anomaly components, right? Two spectral components, but very difficult to resolve. And for that, we need derivatives for spectral resolutions. Here is that spectral resolution that have been checked. This one is a first order derivative, which has been computed with a finite difference, and another is with a Fourier transform method. So this is a first order, this is a second order. First order derivative with a finite difference, and first order, second order derivative with the finite difference, first order derivative with the Fourier transform methods or Fourier spectral methods, second order derivative in Fourier spectral method. When data contain no noise, that difference scheme and Fourier spectral methods are very good. You see the synthetic data, which is red, and estimate data, which are blue, are basically fitting. And it looks like that difference scheme is doing slightly better in terms of their fitting error. But overall, both performance is acceptable. But what happens when the data contains noise? Very small noise, 40 dB SNR, means signal to noise ratio, means around 1%, around 1% of Gaussian noise. So AWGN is an additive white Gaussian noise. If I put additive white Gaussian noise, you find that left-hand side, the blue is the estimated one, the red one is the true one, and you see that Fourier spectral methods, things are absolutely unacceptable with a delta lambda 0.25 nanometers. This is also the case of the difference scheme, central difference scheme. And with this, keeping this delta lambda, that means the resolution, there's a sampling interval, 0.25, even difference schemes also not doing very good. But if I increase that one, that's that means central, the grid spacing, sampling interval, larger, 4 times, like 1 nanometers, then things are improved a little bit. Because with the difference scheme, it is a kind of regularization. Larger the sampling interval, regularization takes place, smoothness takes place. So that's why things have been improved. Let us see another case. See here, we have the prisms, again the same type of things, prisms, and right hand side are gravity anomaly with noise, very small amount of noise, 35 dB SNR. 35 dB SNR will be around less than 2%, 1.75, something like that percent. So less than 2% additive white Gaussian noise. And see the situation, second order derivative, gone. You cannot see. That image becomes so ugly. That's why I say how beautiful that La Villa turns ugly. So a small noise in the data exaggerate so much, overwhelm, that you do not see any resolution anymore, which was with a no noise, highly resolved. Now with a small noise, gone. So noise is the biggest trouble, which has a toll on the robustness of the derivative estimations. Why such things happen? Say, suppose this is a situation, fx, that you measure the data. F curl x is the measured data. Fx is the smooth function. So you always consider that my data is somehow related with some smooth function, and hx is a noise component. So when you use that first order derivative, then there are two types of error exist. One is called the consistency error, which is due to that precision. Basically, if you increase the order of derivative, then precision become more and more. Another is the error due to noise, which comes expansion. So if you see that this figure here, that with the different things, this line, the consistency error is falling as we lowering my grid interval. So grid interval, as long as grid interval is going smaller and smaller and smaller, consistency error or the accuracy is improving. But the perturbation error is going up. That's what is happening. That's what we saw. That when that grid interval becomes larger, that the things becomes improved. So that is the biggest problem. That means you cannot measure something which is with a finer grid interval where noise becomes important. But if you do that, then you have to ensure robustness in computations or estimation of derivative. So to address the issue of robustness, why it has happened? Because noise created loss of smoothness. Noise can be considered as a wiggles over otherwise smooth functions. So the remedial measure will be that to impose smoothness. And how to impose smoothness? Impose smoothness requires filtering the noise, which is unwanted. They are just like a gate crasher. They just enter and created the mess. So for that, there's one kind of very nice filter. It's called the Savitsky-Golay filter, which is basically an FIR type 1 moving polynomial filter, which has been developed by Savitsky and Golay in way back 1964. Both are working at one was working at the university, and Golay was working with that laboratory, with a drug laboratory. Anyway, so this filter is a pretty old development, but many people doesn't know. In 2011, that Professor Schaeffer is a doyen in signal processing. He told that in a seminar that only 20 out of 100 people knew about the Savitsky-Golay. So in the seminar at USA on signal processing. So even if it is highly used in many places, many people even doesn't know about that Savitsky-Golay filter. So the filter has the following attributes. It locally interpolates data with a moving window, something like Euler-Deacon type of things. Essentially type 1 low pass FIR low pass filter. It is a very most important thing is that it created minimum distortion while reconstructing the signal, returns reconstructed data and its derivatives simultaneously, and computationally very tractable, very easy to design. So keeping these things, recently I have developed this design of that SD derivative filter, which has been presented very recently, a paper at Geophysical Prospecting, you can find. But the filter design is a very important thing. There are two important parameters, polynomial order and the filter length. That means the window size, something like akin to the window that normally we use, say Euler-Dicon or Werner-Dicon type of things. So here is also a window you require. So for that, following are the steps, like get an a priori estimate of the noise level, eta in data. You need to know what is the noise level. If you know the noise level, then choose the polynomial order P and what will be the derivative, say first order or second order, accordingly you choose. And then you measure the filter length L, which is in terms of the sampling interval. So this is the formula. And then you go on doing these things and optimization type of things where you try to make the results with an appraisal with a Darwin-Watson statistics and Derringer switch desirability functions. The details are in the paper. I am not going to discuss about the Darwin-Watson statistics or Derringer switch desirability function. These are there. These very important things of optimality conditions. So, and then on the test analysis satisfied, you get the polynomial order and the filter length. These are the two parameters, very important parameters that you select and then use it for estimation of derivative. And here is that some result. So we use the Gaussian pulse because Gaussian pulse is a very ideal situation because majority of the anomaly looks like that, and Gaussians, you can compute your first order, second order derivative analytically. And in that, your FWHN is the full width half maximum, a pulse normally being having an attribute of the two things. One is the peak amplitude, another is the full width and half maximum. That is this width, which talks about that pulse shape. So keeping these two parameters fixed, you see, this is the results. So we find out with this filter length that with the polynomial order, say keeping 3, these are the situations, first order and the second order. With the polynomial order 5, the first order and second order, see the things are improving. And with the 7th order is a much better result. So these are the, which keeping that filter length as same as full width and half maximum, and increasing the polynomial order, we find that better and better results are revealed. That means the robustness is there as well as fidelity. That means spectral content of the anomaly being preserved. But this is the case with a very mild noise. Again, we conducted the same thing with a noise, now with a higher noise, 25 dB SNR. 25 dB SNR is sometimes something around 4.67 or around 5% nearly noise. And then we conducted that statistical appraisal. So DW is a Darwin-Watson statistics. If it equal to 2 means data is appropriately fitted. If it is greater than 2, then data is underfitted. And if it is less than 2, it will be, oh, sorry, it is an overfitted. It should not be underfitted. Sorry, it will be overfitted. And lag1 autocorrelation coefficient, which is the Darwin-Watson statistics, ρ1. If it goes to the positive value, then normally this, due to the filtering process, the random noise transformed into a red noise. Red noise having a spectra is having a low frequency part. So when it is a negative, it becomes a blue noise. When it is towards 0, then only it's a random. And DF peak, DF is a Derringer that switch desirability function. DF means desirability functions. So with a 0.993 for peak value, and for FWHM means full width half maximum, which I consider as one of the parameter for pulse shaping, and that becomes 0.95, together it becomes 0.97. So what we found that in this table, that when polynomial order is kept 3, when the data is having a noise of 25 SNR, then filter length to increase by 23 number of samples, then Darwin-Watson statistics is very close to 2, and autocorrelation coefficient becomes very near to 0. That means it's fitting, and RMS errors is within that, is around that 4% of the trend. So we use this one for the higher noise with 25 dB noise, and we checked with that increasing that keeping the polynomial order fixed, how the filter length is increasing. So lower the polynomial order, you lose the fidelity. Higher the polynomial order, you gain the fidelity, but at the cost of noise. So there is an optimality. That means what would be your polynomial order and what will be your filter length. So keeping the polynomial order 5, the filter length, it is a test of filter length. So when the filter length is 1 of FWHM, that means equal to the full width with half maximum, then it comes this. This is the noisy data. This is the first order derivative. This is the second order derivative. When it becomes 1.5 times of full width half maximum, this is the first order derivative. This is the second order derivative. When it is a 1 3/4, 1.75 times of full width half maximum, this is the first order derivative and second order derivative. So keeping these things and all the statistical appraisal, you can choose what should be the polynomial order and what should be the filter length. This SG derivative filter can be used not only with a 1D situation, but also in 2D. And 2D polynomial that I'm showing here. And this most interesting thing, the coefficients of the polynomial that A00 become filtered data, first order derivative A10 in X, A01 in Y, and therefore you can measure the total derivative. And these are A20, second derivative, and 0.2 second derivative in Y direction. One is X direction and the Y direction. So with these things, you observe that with a very small noise, this is the data, that is an anomaly response with a little bit of noise. And then this is the one, is the synthetic one, the filtered one. And you see that filtered results are very good. This is the first order total derivative. It is a vertical derivative. And when we do it with a Fourier spectrum, the situation has gone bad, worsened. So filtering techniques, Savage-Gray derivative filter for 2D case generate a very robust estimate of first order derivative. Can we do derivative estimation by other means? Yes, we can. We can do by regularization technique. Here I developed some regulation technique which is based on the concept of antiderivative. You know, derivative and antiderivative, as we learned it in the school, that if a function fx has a derivative, then if this is, then we can have an antiderivative. So within this concept, you can generate a matrix equation where A is the operator and F delta is the actually data sets, and U will be the derivative. But for solving such matrix equations, you implement the regulation technique where there is a constant used. This constant is basically the constant of containing that how close that the data is fitting with the, that estimate is fitting with the data, at the same time removing the wiggles of the noise. So the constant is a physical constant, in that we consider that due to the presence of wiggles, there is a increment in the curvature of the curve. So therefore, we reduce the curvature, and that D is an operator for that. You know that this type of concept has been used even by Briggs for generating the smooth functions or generating that from discrete data, the map. Almost the same consideration, but the approach is different. So in that, this is the one which is fitting the response, and this is the one with the keeping the physical constant. These two has to be balanced, and we balance it by a regularization parameter, which can be chosen with this formula. This should be alpha stars anyway. So this is this psi alpha is this one, the constant, and phi alpha is this one. So where nu is suitably chosen, normally it is less than 1, some value 1/4 of 1 is the 0.25 is the right value for that. But regularization works fantastic. You will see. This data with a noise, very small noise, Fourier spectrum with the first order derivative unacceptable, with a different scheme is also unacceptable because blue are the estimated derivative, and regularization one is a fantastic, and it's resolving the it's preserving the resolutions, preserving the spectral content at the same time getting the derivative. So what we observe that with some kind of filtering like SD derivative filter or by regularization, you can bring in robustness at the same time, keeping the fidelity, data fidelity intact. So do we have an example? Yes, very recently it has been published in the journal that how a SP anomaly for a thin sheet model with using derivative-based interpretation. Direct, you do not need any inversion. Directly, you can get derivative. Like this is the data with the Bavarian wood SP anomaly. And interestingly, the points, this is the first order derivative and second order derivative. The 0 points, 0 locations will give you, will allow you to determine the parameters. What are the parameters? Parameters are the locations of the buried sheet, depth of burial, depth extent, then inclinations or the deep of the body. And most importantly, if you can have a robust estimate of derivative, zero finding mechanism is a beautiful mechanism where you can use a root finding methods and everything will be automated and your interpretation will come quickly, just automated way. Do not need anything. And you can also do it, if you do not have other means, you can do it in the field by plotting this one. Also, you can do with it just simply by plot. Next, we talk about that emerging concept. It's very important. This regularization, this derivative, it is there. There are a huge amount of publications are there in this field. And I also had put some work on that area. I have published some of these things in the Journal of Computational Physics, Journal in Geophysics and Geophysical Prospecting to get a robust estimate. But what is most important these days is the emerging concept. We need, we are talking about deep learning. We are talking about machine learning. So in that emerging concept, new approach we call automatic differentiations. And there is a new concept is coming, which we call the dual numbers systems. Dual numbers is somewhat akin to that imaginary numbers. It's not exactly. The method was developed in actually the late 19th century, which was by Clifford in 1876. This concept came first, and William Clifford, something around 1873, it was there, but it was never been used. Later on in the beginning of the 20th century, the first time dual numbers has been used. So what is dual numbers? Dual numbers says Z is a number, like an imaginary number, where A is the real quantity, B is another quantity, and epsilon is a very small perturbations. In such a way that epsilon squared, epsilon cube, and etc. higher order terms all are 0. And then you make a conjugate, something like that with the imaginary numbers. And then if what would happen that if you multiply this Z with the Z dash, then it becomes A square. And what is most important that if you implement this dual number concept, then a polynomial, which is very simple, smooth functions with a dual number concept, what do we find? That polynomial value and its derivative. So implementing a dual numbers, you can making a epsilon as small as possible, you can get that derivative calculation highly precise. And this is very important. This is very important for the sake of the sensitivity analysis, for any kind of things where precision is most important. With this dual number concept, another important thing that you have to add with, which is called the computation trees. Like, what is computation tree? Suppose U and V are the two inputs, and say plus and multiplications are the two operators. Then U and V with this, you can generate a tree with, say, A is equal to U plus B, or with the product W equal to V, then you product another and output becomes this one. So if you can go forward way, then from output you can get this one, but you can, from there, you can go backward way. So if you can make an algorithm where there is a forward and backward iterations can be done, then derivative computation becomes automated. This strategy being used these days in what we call an algorithmic differentiation or adjoint method. So suppose adjoint method is called, suppose X is any computational grid. Suppose you make a finite difference grid. Suppose you want to calculate that map and use the physical quantity to be estimated. Then, and if you have a model, say M with the say P parameters, so it starts with M to, you go to X, that is for X, you compute U, use the physical quantity, and you want to have A, an operator, which is a basically sensitivity matrix or the Jacobian. So you can go this way for a part. M1 is the, say, derivative with respect to model parameter M1. So if you do this way, then you can calculate the derivative, and you can go in the reverse. Then you require only its adjoint. Adjoint is basically an operator, which is kind of operator which is coming mostly with the derivative, mostly with the vector as well as the matrices. So this kind of operation, if you can do this kind of operation, then the derivative computation becomes automated in the machine. With this concept, these days are being developed with a neural net topology. This concept of neural net derivative computation was not new. It's almost 3 decades back, but but modern days that deep learning, machine learning are so a buzzword being used. But this concept has been developed long time back. Was basically Kurt Hornig was the persons, and his Kurt Hornig and his colleagues, they developed first this neural net based derivative. So what is neural net based derivative? That neural net, let me give you a very brief descriptions. It is basically neurons. There are 3 types of neurons. One is the input layers, one is the hidden layers. These are the blues, the hidden layers, and output layers. And they are connected with the network topology. And you put the data here, and this hidden layers compute with this using the weight function and activation functions, and it gives the output. But you require certain amount of training. That is where there is these hidden layers are being trained, and this process, if you from left to right if you go, this is called the feed-forward neural network. And this, where the process will be as a black box, hidden layer is a black box, works and with the activation energy and the weight functions, and then automatically it computes. So if you change the activation function, which is normally a tan inverse X or this type of is a asymptotic, is a S-type function, and if you take a derivative, it is basically the same. So if you change this activation function, you can automatically compute with the feed-forward network the derivatives, provided your network is trained. And for network to be trained, you have to choose some optimizations routine in that. So these are the actually are the diagrammatical presentations how the neuron works, like summation for summation, pi for product, and there is one input, another input, and then it's coming in the next neurons, and that's the way it goes. So possibly there's had enough of mathematics and that, and some may be feeling exasperated with the situation that going much detail with the mathematics and technical things. But if you are, then possibly this quote will help you, which is John Louis von Neumann, which is the greatest computer scientist, mathematicians, and computational methods who has worked. His comment that people do not believe that mathematics is simple because they do not realize how complicated life is. So with that, I end my talk. Thank you very much. I hope that
very much,
I am
Indrajit.
finished within that 5:30 timeline.
Yes. Can you hear me, Indrajit?
Well, I could not hear anything. So
Can
if
you hear me now?
Then Q&A. I opened Q&A, but I cannot hear. That is the problem. I can only chat. I suppose I can do that. I do not know how to do that, chat.
I think it's best if anyone has any questions, if they can pop that in the chat feature down the bottom, then we'll be able to communicate with Indrajit to get his answers.
Yes, I'm in the chat window because I cannot hear. Would you please just give the questions?
Well, look, thank you very much, Indrajit, for a fantastic deep dive into derivative functions there, some of the emerging concepts, the pitfalls.
Thank you very much.
And particularly the understanding of your noise before you go ahead. I have a couple of questions for you, but as Laurel said, if we open it up to the audience, and please put your questions in the Q&A box, not the chat box, please.
Hi, Asborn. Hi, Anandudu. I heard about you, but I never met. If you have any question, please in the chat, because I cannot hear. I can only speak, and I can. So if you can send me the things I can speak, I possibly will listen that, and I can. Thank you, Mark. Thank you. Thank you. Thank you very much. Well, this is, I'm working on, I'm developing some of the stuff.
There's one
and, well, and I'm also writing a book on that. But this kind of things, very difficult. Sometimes you may get it from people from the university. Oh, that's great. Graduatory work. Well, you know, in the graduatory, there is a very noisy things. And, you know, I have done a little bit of work on that, how you can change from graduatory to data to the anomaly. They say reverse process integrations. Although it sounds very easy, but it is not easy either. And not really, not really. I have not tried Adams for Autodeep. No, not really. Hi, Yvette. How are you? Hi, Kullan. Thank you, Kullan. Thank you. Uh, dear Anandarup, I have not tried Adam for Autodeep. No, not really. I do not have the software's availability. I'm a lone scientist, a loner. You can say that I do it myself. So computationally tractable means easy to understand, easy to get into that, because it's a very simple filter. Savitsky-Goulet is basically, you can use an algebraic equation, polynomial, like a power series. So very easy to understand, easy to implement. That's what tractability means. Yes. Bob Musgraves, our geological survey mapping geologists are always keen on second derivative TMI, but we are often defeated by noise. I'd be interested to see how your filtering approach would go. Wow, great, thank you. I believe it will. Both that Savitsky-Goulet derivative filter, which is really very good, very powerful, and actually I have written a paper, not yet communicated to the journal, where I have used Savitsky-Goulet derivative filter for second derivative, and it's coming fantastic, beautiful results. But I have not yet communicated to the journal because I have some more works that are going on. But I'll be more than happy to discuss with you, Bob, for second derivative, generating of second derivative TMI map, because it is very important. It can give you that identification, age identification, fantastic way. Oh, Anand, Mike Barlow. Also a more general with your Mike Barlow asking these questions, a more general question. With all your experience, are you finding that increasingly scientists, including geophysicists, have no fundamental understanding of derivative functions and their pitfalls? No, people are much smarter than they know that. Mike, scientists in the geophysics have in fact they are people, but some professionals do not know how to tackle these things. That's the reason that that so many of publications on derivative estimations, robustness, you will find even in the Journal of Computational Physics, so-called high-end physicists finding it sometimes difficult to get the robust estimate of derivatives. So you find many publications on still going on how to improve that robustness of derivative, because show you the use of noise, of random noise, but there are many kind of noise, and some noise characteristics are not known, and therefore derivative estimation becomes a challenging problems for many of the situation. Moreover, if data is very scattered, heavily scattered, if it is heavily scattered, derivative estimation becomes a very challenging problem. So even when people knows about it, solutions are often becomes challenging. Is it, I think, does it satisfy you, Mike? My answer? Mike, also a more general question. With all your experience, are you finding that increasingly scientists, including okay, sorry, thank you, Indrajit. Apologies that I cannot close the webinar. Thank you again for presenting such a deep dive into derivative functions, the pitfalls, and the importance of understanding your noise. Yes, all good. Thank you, Mike. Thank you, my dear friend and peers, and ladies and gentlemen, to attending this webinar. If any of my message goes and helps you in your pursuit of scientific investigations, I'll be very, very happy. I'm a lone scientist. Basically, I do not interact much with the people. I work myself and working on that. I'm also doing some more work on a different kind of, I have not mentioned those type of work. This is called that topological derivative, which is a even very high-end derivative concept, mathematical concept. It's still in the mathematical domain. Well, I wouldn't say it's mathematical domain. It's still, people are using it in the image processing, and it has got a huge potential for potential field image processing, because finer structure, very finer structure can be come out with the topological derivative. But implementation of topological derivative is quite a challenging task, both in mathematical rigor as well as computational point of view. I'm working on that. Maybe sometimes I will discuss. Thank you. Oh, Kullan, you have said the seismic wants multiple use tagged, to be tagged as noise, but now it also used as a signal. So you think that kind of opportunity in your second derivative postulates? Well, maybe I do not know. I cannot say you with certainty because I have not experimented these things with the seismic yet. And therefore, I cannot say with a guarantee how will it work. Maybe it will work. I need to know it. I need to find it experimentally, at least numerical experiment. I have not done it. Sorry, I don't know whether it will satisfy Kullan. Any more question, please? The problem is that I cannot hear. If I could hear, then possibly it would have been good, but I cannot hear. I can only talk and can respond to this computer screen. So, Mike, if you find that it's all right, you can come to the screen and maybe you take the dash or you take the podium. There's no podium here, virtual podium. You take the charge of that. Oh, Musgrave. Sorry, Bob. Sorry. Here is a repeat of my question. Sorry. Let me come to you. Thanks our geology second derivative, but we are often defeated by noise. I would be interested to see how your filtering approach would go. Well, sure, Bob. Sure it will be. I'll be glad to use your tackle your problems if the situation arises. I live in Canberra. Now it is a COVID-19 situation, so only thing we can do over just by virtually contact. But if things improve, maybe I may come down to your place sometimes, and you can see. That's not a problem. Hi, thanks for your talk. I work with gradients all the time in getting to work. I have found a lot of trouble with Euler, even when using smooth grease, due to vertical stacking of solution. Well, as you know that, Euler deconvolution there are two kinds of problems. First kind is that derivative estimation has to be perfect. And another thing is that you know that your Euler optimum window is very important, okay? And Euler deconvolution is a problem where the solution just sprayed. It just sprayed all around into the, say, for 3D Euler 3D space, for 2D Euler in 2D space. That's a big trouble with Euler deconvolution. But I have a work publication in Geophysics 2017, where for 2D case, the results is spectacular. For you do not need an Euler deconvolution for 2D. I have not checked it for 3D. But 2D, you do not need. It will give a spectacular results with using derivative. Please, I have not shown that slide in this because of time constraint, but you can see my work in 2017 Geophysics journal, where I've used derivative-based interpretation for that regular shaped isolated geometry body. And that gives a beautiful results. Oh, Bob, thank you very much for your kind. I sure I will. I like to see you people. Sure. I am most of the time confined. I'm a very loner, you know. I am a lone scientist. I confine myself within my four wall and work. Not much interactions I do, but I surely come sometimes to your place and tackle the situations if I can do. Thank you. Thank you.
Okay, thank you again, Indrajit. We might leave it there.
Is there any more question, please?
What?
Please carry on. I am ready to answer. I have no problem as long as Mike allow you to continue. Thank you, Mike. Thank you. Thank you. You are a very kind man with a huge patience.